Okay, I'm Malcolm McCallum at Langston University in the Department of Agriculture and Natural Resources, and I'm presenting on some research I've been working on over the last year or so. So this is about extinction of turtles and where we're at today. And so first, because there may be some people watching this that aren't scientists, extinction is, of course, permanent loss of species. Before 1813, extinction wasn't a given. It was thought of as kind of a possibility. People were debating whether things could really go extinct. And then Cuvier published his essay on the Earth, and of course, since then we've accepted that not only is extinction possible, it happens, and that the fossil record is that the fossils aren't just curiosities, as he put it, but they are, it's an important ecological and evolutionary process, and it's often confused with extirpation. Extinction is, it's gone. Extirpation is just a regional loss. So every species lasts about 4 million years on average based on fossil record. We know that most species that have existed have gone extinct. We've had about 4 billion of them. And that it's around that only about 1% are still extant. We can categorize extinctions based on 1 million, 10 million, and 100 million year events. These are minor, major, and mass extinctions. Of course, we've only had 5 or 6 mass extinctions in the history. There is some debate about a very, very early one. And these extinctions have involved a lot of very broad groups of organisms, or whether you're talking about placoderms or ostracoderms or dinosaurs or what have you. Each of these mass extinctions, the Ordovician, Devonian, Permian, Triassic, and the Cretaceous, were all 1 in 100 million year events. These were not things that happened very frequently. And they often spanned a lot more time than we think of. From a human perspective, these are huge amounts of time. Geologically, they're relatively small. Of course, the Permian Triassic, it could have lasted as much as 9 million years, depending on how you define what the Permian Triassic extinction is. Some people divide it into a major and a mass extinction. Some people combine them together, and they go back and forth on this throughout time. Of course, the Jurassic Triassic probably actually lasted about 500,000 years. While a lot of species went extinct initially, it still had species disappearing for quite a while, up to 2.75 million years, depending on whose estimate you follow. So background extinction, though, tends to be more selective than mass extinction. That's extinctions we see all the time. Oftentimes, background extinction is balanced out by your typical background origination, which is the evolution of species. Background extinction, you see specialists go extinct, especially highest, super specialists that have real fine details in their life history, where generalist species tend to keep on going because they're very much more flexible. Over time, this just is to show you how background extinction on the yellow line relates to variation in overall extinction. So, I'm just trying to see something here. I do not have a chat box up. I cannot get it to come up. Our mass extinctions tend to be caused by abiotic factors up until recently, and that's because we are really causing it, even though we are causing geologic factors to occur. They also tend to be not very selective. The most recent mass extinction, of course, was the Cretaceous Paleogene extinction. Previously, we used to call that the Cretaceous Tertiary, but that isn't actually accurate because you're comparing you're using border of a smaller time period with a large, and you want to use the same time period category. About 76% of the species actually went extinct. Of course, the dinosaurs, even though a few dinosaurs may have lasted into the Paleocene, that's under debate, but it's reasonable to think that could be. But unlike these previous extinctions, we basically have one species causing most of what's going on today. When we look at turtles, as of using the IUCN data on the Species Survival Commission, we see that we have approximately 8 species that went extinct since 1500. And these numbers may be a little off, depending on whose estimates you use. Extinct in the wild, critically extinct, endangered, in the different categories. Right onto data deficient, and of course, different levels of extinction, whether it's extinct in the wild, and so forth. It's important to realize that on fossil standards compared to what we see all the animals that exist or all the plants that exist. When you go into the fossil record, when ranges contract and abundance declines, the probability of extinction remains the same, and so you have them disappear from the fossil record before they disappear from the planet. Organisms that we count maybe 10 or 15, 20, 100, 1,000 species, individuals left, those aren't in the fossil record. They're already extinct. And they're classically called dead clades walking because they'll appear in the fossil record in a punctuated fashion. Just occasionally here comes a fossil, but there's no evidence of it being there before. Because we have this variation we have a lot of uncertainty in our data due to the fossil record, and also we have uncertainty in modern data because of issues with being able to revisit places. We actually have a much more, I won't even go there. Because of this, when you're dealing with a lot of uncertainty, there's different ways to deal with it. And one of these that's very appropriate for paleontological data when comparing it with current data is using fuzzy mathematics. And what fuzzy mathematics is basically is this. If you think about a point estimate, which most of us use every day, we try to get a very exact number of how many people are in the room or whatever that is. And, you know, a lot of times point estimates aren't all that important. Whether it is 33.235 whatever milliliters of fluid in his drink, or if it's 34, is it really irrelevant? Does he need to have his drink topped off? We don't know, because I don't know what the volume of his cup is. But we take a system like this, we're a wee bit low on the beverage, we right away know that we need to get some more. This is how fuzzy math works. It's giving you the trajectory. It's telling you that, hey, this is somewhere over here. It doesn't mean that an exact number in there is somewhere in that group of numbers is the right number. The bottom line is the stuff outside of that set is not accurate. If you're trying to say there's no difference, and the fuzzy set showing enormous differences, saying there's no difference is complete bunk. It's not going to happen. We've all seen fuzzy estimates when we watch the hurricanes come into the coast. That cone that they show coming in, and over time they narrow it down. That is, in fact, a fuzzy estimate. So looking at the two, we can see that there are times when having the exact number is really important. But there are times when it's important to understand what's going on, and whether it's 2 or 3 doesn't matter. So from a mathematical perspective, it's set up like this in a distribution. We have things that certainly aren't possible. They get a value of 0. Things that are possible get a value of 1. And then we have things that are somewhere in between. And so on a graphical presentation, our fuzzy numbers tend to be triangular or parabolic in the system that we're using. They don't have to be. They can be wavy lines and all kinds of stuff, but that's more for people who are doing computer science and not for practical stuff like we're doing in this study. So then you get a set that has the borders, A and B, and then of course the middle set is the stuff that's most where we expect it probably is. And as you go from the M's to the A and the B, it's gradually becoming less of, those are things we can say are probably not true, but they could be. They're borderline. And we get a fuzzy interval like this. Fuzzy arithmetic's ideal for this, for looking at things where there's a lot of uncertainty, extinction estimates for sure. And that's about all I'm going to say about that. So how do our extinctions today compare to what we've seen in the fossil record? Well, there's a lot. I broke this up to modern extinctions since 1500 and since 1980 because we have some different things happening there as technologies improve. And so we compare it in that way. That's the standard way that people who've been doing this kind of research have been doing it. So we have all these extinction estimates based on places all around the world, a lot of them in the US, but also in China and other places. And then there's a series of standard equations that are found in conservation biology books and that for doing this kind of thing. Okay, so when we start, oh my goodness, I think am I on the right one? Wait a second. You know what I did? No, that's right. Okay, I was just double checking that I was in the right place. So as we go here, we can see that different groups have gone extinct as of since 1500 at different rates. Okay, now, but if we look at our turtles have gone extinct right here. This is what we expect, somewhere between 87 and 658 times what they did, what reptiles went extinct at Cretaceous Paleogene. And that's telling you, now, that tells you a lot about what's going on. Again, since 1980, they've gone extinct much faster. Even now, this is considering that I'll go on and I'll continue this. So remember that when we look at the IUCN data for turtles, it's a little bit different than what the TSA has posted. But the bottom line is that when we look at these numbers, they actually are comparable. And that's what we really want to look at. If we start adding in organisms that are dead clades walking, that are currently extinct, but they're going extinct, or we may be able to revive them, but they certainly are in very small areas and they're very endangered. We find that these numbers go grossly out of insane. This is the same kind of information, same kind of numbers we're seeing for other vertebrates, the same kind of numbers that Barnowski saw with Ehrlich and Sabalos, and the same kind of numbers that Pym has demonstrated. And in fact, when Barnowski put out his data using interval assessment, he actually came back and recalculated it, making assumptions more narrow, just because people were complaining because the numbers were so high. As we look at this, so what would this mean for the sustainability of turtles? How long would they last into the future? And of course, at the 1500 rate, we're talking about 1,000, less than 1,000 years. They certainly aren't going to last forever. They're not going to go extinct tomorrow. But when we look at the post-1980 extinction rate, we're talking about you could have them all go extinct that fast in 59 years. Now, the key here is that these numbers, the reality when you actually look at it, some species that are just like, red-eared sliders, they're going to hang around a lot. But a lot of your specialist turtles could disappear relatively quickly, especially as climate change ensues and so forth. And that we know that climate change, increased temperatures, messes with their physiology like mad. So a live animal may be sitting here and reproductively the population can be dead. So the conclusion, of course, turtles support the previous papers that have been done. And of course, that's basically where I'm at.